Hello students, my name is Shashank Shekhar and today is the fifth lecture of the chapter Alcohol, Phenols and Ethers. So if you look at the syllabus here, so we have covered up till this preparation of phenols, and today we will be looking at chemical properties of this phenol. Right, now we have covered the physical properties of phenol in the previous class. I think when we are doing with the physical properties of alcohol, then we also discussed about the physical properties of phenols and the physical properties of ethers. So I have done so because that could make a good comparison. Then moving on to this today's topic, that is chemical properties. So we'll cover this today. Not only some of these reactions we will cover today, and some of the remaining one we will cover tomorrow. Okay. If we talk about the chemical reactions, so we will talk about this electrophilic aromatic substitution reactions, right? Then about this acidic nature of your phenol, we will see this tomorrow. Okay. So let us start our today's lecture. So here are the topics of today's lecture. So we have seen that simple alcohols react with your acid anhydride or acid chloride or carboxylic acid to give their corresponding ester. Now the conditions can be different. Like for acid chloride, we use this pyridine, that is base catalyzed reaction. But for the other two, that is acid anhydride and your say carboxylic acid, we use the acidic condition. So I have mentioned this esterification again in this lecture because I will perform a reaction to make a specific product that is useful for our daily consumption. Okay, no, I would not say daily consumption, but in our medical life. Okay, medical application. It has a medical application. Then we will see the mechanism that how we will make that pharmaceutical compound. After doing this, we will see some specific reactions of phenols that would be like our electrophilic aromatic substitution, under which we will see nitration and halogenation. Then we will see reaction of phenols with zinc dust, which is basically a redox reaction in which this phenol gets reduced. After this, we will be left with two of the reaction, that is coal-based reaction and Rimmer-Timmer. So they both are very important. So we'll see that in the next lecture. If we have time, then we will get to it. We'll see some conditions regarding that reactions. But for now, we will focus up till this reaction of phenol with zinc dust. So starting with the lecture, first we have esterification of reaction. So in the previous class, I have shown you that how this mechanism, all this mechanism goes. So I'm just putting up this slide to make you a quick revision, to make a quick revision of all of this. So it was of three types. First of all, if you react your alcohol with carboxylic acid, which is acid catalyzed, then you will get your ester plus water. Second, if you react your alcohol with acid anhydride, under same acidic condition, but in this case you will get your ester plus a carboxylic acid, and the reasons are obvious from the reaction mechanism. At last, we will treat our alcohol with acyl chloride. So I would suggest you, and I will make you learn also when we will see this carboxylic acid, that is aldehyde, ketone and carboxylic acid. In that time, I will make you see the derivative of carboxylic acid, like our acidic anhydride, like our amide, this acyl chloride. So you should try to remember all of these derivatives of carboxylic acid because they are important in solving the questions. So in this reaction, we will use base, not acid. So base will act as a catalyst here, and we will get your ester plus HCl gas. One more important thing about this reaction is that in all of this reaction, they are reversible reaction. So reversible reaction can also move in the backward direction. Therefore, first one, this one, water is removed to facilitate the forward reaction according to our Le-Chatelier principle. In this one, we are using this pyridine. Now this pyridine neutralizes the released HCl and therefore reducing the product concentration and hence facilitating the product in forward direction in accordance with our Le-Chatelier principle. Now we have mentioned here that in place of your say normal alcohol, that is ROH, we can also use aryl alcohol, that is phenol. So here we have put up a reaction here. So it is a derivative of phenol which has a carboxylic acid substituted at ortho position. So we will do the acetylation of this group OH by esterification. So we know the esterification reaction. So this is now this compound that is having having carboxylic acid as ortho position. It has a common name. It's very popular. That is salicylic acid. Okay. Now this salicylic acid is made to react with our acid anhydride in the presence of acid H plus, that is I think H2SO4. You can use any acid. So in that case, you will see that esterification of this OH bond is done with this anhydride to get our ester. This is ester. So if you just expand this thing, it would look like this. Okay, this one will be here, and this thing, yes, plus our CH3COOH. So since we are using our acetic anhydride, so we will get acetic acid. So this length of this acid will depend upon the anhydride that we are using. Suppose if we had been used this C2H5 instead, then we would have got this as C2H5 COOH. Okay, so the nature of this acid will depend upon our acid anhydride. Clear? So this is the reaction. Now during this reaction, the product that we got on acetylation of this OH group. So if you look here, so we have done the acetylation of this OH group and introduced our ester. So the product that we have got is called as aspirin, and you must have heard this term aspirin. So it is used during your heart attacks and all, and it's say one more name it got from its derivative, that is it is a kind of derivative of salicylic acid. So it is also termed as acetyl salicylic acid, because we have introduced the acetyl group here, CH3CO. So basically this CH3CO is called as acetyl. So the name we got is acetyl salicylic acid. Okay, and this is called aspirin, and it has a very you can say wide use in this pharmaceutical industry. Now let us see the mechanism of this for the formation of this aspirin. So you can see clearly that it is esterification. So we'll see the mechanism here also. So first of all, what will happen, since we have used this acid catalyzed, or we can say since we have used acidic condition, our anhydride will be protonated first of all. So if this protonation occurs, this will increase the nucleophilicity of this center. Now the your alcohol will just donate its electron to this nucleophilic center, and it will result in this kind of intermediate. Okay, now this H, since it is acid catalyzed, this H will be removed by your A minus, and your H will be removed. Okay, in this way. So we got our H plus concentration back. So we are left with this. Now this is very least stable because it is a kind of acetal. Okay, it is acetal, and acetal are not stable, because this C double bond O is found to be much more stable. Therefore it will just release this group. Okay, so first this H is again taken by the acetal group, and this is released in the form of your acetic acid that we have seen, that is CH3COOH. So in this way you got your acetic acid, and the ones we are left with is this. It is in a protonated form. Again this H will be removed by deprotonation, and we will get our required product. Okay, so clear? Is this clear to all of you? So in this way we can see the mechanism of this acetylation of salicylic acid. So if you just concise this mechanism, then first of all the protonation occur, second is the nucleophilic attack on this protonated acetic anhydride, and third step is the removal of acetyl group. So I have just summarized all this step as the removal of acetyl group. So the most important, I would say, the step would be your nucleophilic attack of salicylic acid, okay, by the OH group. Clear? OH group of the phenol. Now this is the acetylation of salicylic acid. So as I mentioned earlier, the product that is formed is called aspirin, and it has wide application in the pharmaceutical industry. It is used during heart attacks. Okay. So this thing is given during heart attacks. Next, we will see now some specific reaction of phenols. So under which we will today we will see only electrophilic aromatic substitution that will involve nitration and halogenation. Okay, and we will see the reaction of phenol with zinc dust. Today we will not see these two and this one oxidation. So we will see it in the next lecture. Okay, so basically the reaction that we are dealing today are electrophilic aromatic substitution and reaction of phenol with dust. So first of all, what is electrophilic aromatic substitution? So if you just break down this terminology, it is attack of an electrophile on an aromatic system to substitute one of the you can say a part of that given substrate. So if we consider it phenol, the reaction that take place on the aromatic ring are electrophilic aromatic substitution. We know it. Now the OH group attached to the benzene ring activate it towards electrophilic aromatic substitution. So it is written here that this OH group, it is the main factor which activates this benzene ring. So you can say that the reactivity or the electrophilic aromatic substitution, you can say electrophilic aromaticity of this group or electrophilic aromatic substitution eagerness of this phenol is more than the benzene. Why? Because now in this structure you can see that a lone pair of oxygen is being delocalized throughout the ring by resonance. So it moves here, this lone pair moves here, makes a double bond, and this double bond moves on this carbon. It creates this type of structure. Again this negative charge moves here, makes a pi bond, and this pi bond makes the negative charge on this position. Again the negative charge moves here and the pi bond moves on this carbon. At last the negative charge moves here and the pi bond is formed. I think the pi bond is gone back to your oxygen and oxygen is again neutralized. Now during all of these steps you can see very clearly that the electron density is being increased on 3 positions. Where? Ortho, because there is a negative charge, but there is not a negative charge on meta, but there is again a negative charge on para and again a negative charge on the second ortho. So there are 3 positions with respect to the phenolic group which are being activated by the phenol's oxygen's lone pair and are more prone to this electrophilic aromatic substitution, that is ortho and para position. So this OH group direct the incoming group to the ortho and para substitution. So in electrophilic aromatic substitution we have electrophile. Electrophile means electron loving. Now since this OH group is increasing the charge density on ortho and para position, that is your negative charge density, therefore your coming electrophile will go to the ortho and para position, and its resonance structure are shown under acidity of phenol. Is this clear? Okay. Now we would expect that now since this ortho and para position has been magnified, or you can say has been electronically abled due to the donation of the lone pair of oxygen, we can say that it is a ortho para directing group. The OH group of the phenol is an ortho para directing group, and now the electrophilic aromatic substitution will occur on ortho and para only. Clear? Now let us see first electrophilic aromatic substitution, that is nitration. So here we have the nitration. So what do? We treat our dilute nitric acid. So we have taken dilute nitric acid. So since this is more reactive than benzene due to lone pair delocalization of ortho and para position or ring activation by this OH group, therefore we do not use your concentrated one. Okay, we do not use the nitrating mixture. It does not require any nitrating mixture to perform the reaction. You know what is the meaning of nitrating mixture? It is just the mixture of HNO3 and H2SO4. But since this is already activated by your OH group, we do not need any such mixture, right? Instead of that, we only need dilute HNO3. So as you treat it with dilute HNO3 and at low temperature, that is 298 Kelvin, you get your O nitrophenol and P nitrophenol. So we get a mixture of ortho and para. So here is the ortho one. Okay, this is the ortho one and this is the para one. So we get a mixture of both. Now, since we for any purpose, so if we require any chemical, we would require it for a special purpose, and that purpose is only fulfilled if we get the absolute structure that we are looking for. So for that, we need to purify it. We have to get only one of this, which is required. And by luck, this purification is easier in case of ortho and para nitrophenol because of the difference in their boiling point. So we'll see why is the difference. So since there's a difference in the boiling point, we can use the steam distillation. So what is basically steam distillation? So if you start boiling this mixture that we got on say treating it with dilute HNO3, this will slowly start to boil and form vapors. So the one with a lower boiling point will start the boiling first and will form vapor first. So what do? We collect that vapor of the first which is being liberated. Then after some time, the second would start boiling, and then we can get the say our vapors of the second one. Now someone would ask that, okay, you said that first this one will be released and second this one will be released, but can it be a case that both of these start boiling at the same time? This is not possible because if you have seen a very common experiment, so if you put ice in a say bathtub, okay, or suppose you put an ice cube in a bathtub and you start boiling it, until and unless each and every ice cube is not melted, you will not see a decrease in temperature. Okay, you will not see a decrease in temperature. Similarly, until and unless all the para nitrophenol is not being dissociated, or you can say evaporated, up till then there will be no, or you can say which one is boiled first. Up till so the first one which is boiled will be evaporated, then and then only the second one will start to boil. Now you will ask, is that always the case? No. So there should be a kind of difference between the boiling point. You can say a significant amount of difference should be there. So since this ortho and nitrophenol have the same, so we can separate them by steam distillation. So ortho nitrophenol is basically it is steam volatile due to intramolecular hydrogen bonding, while para nitrophenol is less volatile due to intermolecular hydrogen bonding. Now first of all, what is this intermolecular? So if you see this compound here, that is orthonitrophenol, there is a kind of hydrogen bonding between the atoms of the same molecule. Okay, so this is the interaction, that is your hydrogen bonding between the atoms of the same molecule. And in this case, para-nitrophenol, the intermolecular hydrogen bonding is between your say molecules of two atoms or two different molecules. So this is a different molecule and this is a different molecule, and there is an interaction between the atoms of first molecule with the atoms of the second molecule. So this is intermolecular hydrogen bonding and this is intramolecular hydrogen bonding. Now it is seen that the intramolecular hydrogen bonding is not that much effective for changing the boiling point as compared to this intermolecular, and it should be clear. So if you want to boil something, you have to break the interaction between two so that it can be evaporated. But if that bonding lies inside the molecule or between the atoms of the same molecule, then that interaction would not be helpful in any way for the increase in your boiling point. But this would be an aid to this force between the molecule other than this van der Waals force, and hence will increase the boiling point of your para-nitrophenol due to intermolecular hydrogen bonding. Clear? So if you start boiling this mixture containing orthonitrophenol and para-nitrophenol, this para-nitrophenol will start to boil late and this orthonitrophenol will start boiling earlier due to intramolecular hydrogen bonding. So we can write a statement that boiling point of orthonitrophenol is less than para-nitrophenol. Why? Due to the presence of intermolecular hydrogen bonding in para-nitrophenol, which is not in the case of orthonitrophenol, which has intramolecular hydrogen bonding. Clear? So this is the nitration. Now, if you use concentrated nitric acid, so I have told you earlier that you have to use your dilute nitric acid. So if you use concentrated in place of that, what will happen? It will result in tri-substitution. You know that each of this ortho and para position are been enhanced, or the electronic charge has been enhanced by the phenol group. Now there is a chance that okay, each of this can get say electrophilically aromatic substituted, but since this phenol is being activating the group at a larger scale, there is also the chance that this all three group are substituted simultaneously, and this case occurs when we use concentrated nitric acid. So in that case we get 2,4,6 trinitrophenol, and the product is known as picric acid. This is called as picric acid, and the yield of the reaction is very poor. So what do? We can conduct a reaction a different way also. So what do? So now picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it into 2,4-disulfonic acid. Okay, so first we treat it with sulfuric acid to form this 2,4-disulfonic acid, and then with concentrated nitric acid to get 2,4,6-DNP. So if you conduct the reaction in this way, then it would be more beneficiary, or the yield will be higher. Clear? So there are two methods to prepare this picric acid. First one is very obvious. So we treat it with conc HNO3, that is nitric acid, and we get our picric acid. The other method is if you treat it with H2SO4, then two of the position are say substituted, that is one ortho and the para. In the next step what you will do, you will just simply treat with HNO3, and all three position will be nitrated, and hence your required product, that is picric acid or 2,4,6 trinitrophenol, can be formed. So this is the first type of electrophilic aromatic substitution of your say phenol. Now the second type is halogenation. Clear? So let us start our halogenation. Now the second electrophilic aromatic substitution type is halogenation. Now this also can take place in two ways. So we will discuss the first one and then the second one. So the first one is if you use a low polarity solvent such as CHCl3 or CS2. So this both are having less polarity. At lower temperature, then monobromophenol is formed. Okay. So why is it so? So basically what happens in this reaction? So you know this is an electrophilic aromatic substitution. Okay, clear? Now, if there is a higher polarity of your say Br2, then there would be a chance that it will accept greater amount of electron. So because if one is having greater positive charge, other will have a greater negative charge, and the greater positive charge will be able to attract, or you can say have a greater electrophilicity. Now I will ask that how Br2 can be polar. So see, Br2 is not polar if it is presented as in isolated form. Okay, but imagine this is an electron cloud, and you know that electron cloud is delocalized, but there is a chance that at any instant this Br2 electron cloud get distorted, okay, and create an instantaneous dipole moment. But if you use a non-polar solvent, that would be not stabilized in any way. Okay, that would not be stabilized in any way. This CS2 would avoid this stabilization of this polar induced dipole, instantaneous dipole. Therefore, it will have a very less chance of being polarized, and hence your electrophilic aromatic substitution will not occur aggressively. Now, the usual halogenation of benzene takes place in the presence of Lewis base acid FeBr3, which polarizes the halogen molecule. Okay, so if you do the usual halogenation, you use FeBr3, that acts as Lewis acid and it polarizes your say bromine bond. Okay, but you do not need to do so in your case of this say phenol, because it is already activated due to the delocalization of the lone pair of the oxygen and ortho and para position. Now, in case of phenol, the polarization of bromine takes place even in the absence of Lewis acid. So, same thing is written. It is due to the effective activating nature of this OH group. Clear? Now, it is a simple, say, electrophilic aromatic substitution. You can just try to draw the mechanism by yourself. Clear? Now, in place of that, if we use simple bromine water, okay, if we use simple bromine water, so it will not, of course, increase the polarity of this, but using only simple bromine water would increase the concentration. So you are using the bromine water. Okay, so we will use in this. So bromine water is basically, what is this bromine water? First of all, it is basically bromine in water. Okay, bromine in water. Now water is a polar solvent, so it will polarize this bromine bond also. And since the polarizability of this bond has been it is polarized more, therefore the chance of its electrophilic aromatic substitution or the aggressiveness of this electrophilic aromatic substitution increases, and hence we get this kind of tri-substituted product similar to our say nitrated product, in which we use concentrated nitric acid and we got a tri-substituted say phenol that was called as picric acid. Here also, if we use this Br2 bromine in water, which is called bromine water, so if we use this thing, then it will quickly react our phenol to give 2,4,6 tribromo plus HBr. Clear? So this is our halogenation. Now, if you ask about the mechanism, it goes through your simple electrophilic aromatic substitution. There is no change in the mechanism. Only the reagent is changed, but the main reacting part, it is always Br. Okay, so this Br will be simply taken up by this bromine, and the negative charge will be transferred to Br, one of the Br, that is the another side of the bond. Clear? So this is the halogenation. So what you have to take care of is the reagent that has been used. So if you use a non-polar solvent like CS2, it will not polarize the Br2, and hence its electrophilicity will not be increased. So how it is so? Because if it is polarized, so one will of course bear a negative charge, but the other will bear a positive charge, and that would attract your pi electrons of this benzene. Okay, so if you use a non-polar solvent, the chance of it getting polarized would not be greater because it will not be stabilized by the solvent. But in case of your Br2 in water, the chance of stabilization of polarized Br bond, so I have told that there is a chance of instantaneous development of dipole. And at that instant, if it is stabilized, then the lifetime of that instantaneous dipole would increase. Okay, the lifetime of an instantaneous dipole will increase, and hence the chance of your electrophilic aromatic substitution will also increase, and you will get 2,4,6 dinitrophenol. That is tri-substituted one. Clear? So this is the halogenation. Now next, we will move to a reduction reaction. So we have left some of the reaction, that is Kolbe and Riemer-Tiemer. We will get back to it in the next lecture. But for now, let us see what is this reduction. So how it is reduction first of all. So we have removed a O here and added nothing, I would say, and added nothing. But we have removed the O here and added electron in a way. Clear? So you would say that okay, H has also been removed from this substrate. No. So if this place will be vacant, it will be substituted by something, and of course it would be hydrogen. So this hydrogen is not being removed from here, it is present in this place only, sorry, in this compound only, but at a different place. But oxygen has been removed. So removal of oxygen is simply called reduction. And since this zinc is getting your oxygen, so it is getting oxidized. So it is a type of redox reaction. Redox reaction. One is getting reduced and one is getting oxidized. So how does this mechanism goes? So you should know the basic nature of metal. So you know that metal are electropositive in nature. They have the nature to donate electron. So what will happen? It will now donate a pair of electron on this oxygen. So it will donate one by one. First it will form the oxygen radical, and then it will form the oxygen, negative charge on oxygen. So it will happen like this, that first it will form your oxygen radical, okay, and H radical. Now this another pair of then will again donate one electron, and you will get these type of species. Now you have O minus and Zn, so it will form an ionic bond. Clear? Now this ionic bond again gets one electron from Zn. Okay, this again gets one electron from Zn, and this bond is again cleaved, and it forms a phenylic radical. It forms a phenylic radical. Now this one is treated with ZNO, and in the pens, sorry, a ZNO is produced because since we have the electron on this oxygen, and again one of the electron will again be donated on this ZNO, and we will get this ZNO. Now this phenyl radical that is being formed will react with your H radical that would have been formed in the early stage, okay, this one, to give your benzene. So overall this reaction is a radical reaction, and the electron donor, that is zinc, is the species that is oxidizing your phenol. So if you want to look at it in the way of electron donation and electron acceptance, then it is also a, say, oxidation reduction reaction. So this zinc is giving electron, so it is getting oxidized. Also its oxidation state is getting increased, so it is 0 and it is +2. Here it is accepting the electron, so it is getting reduced. How? In two ways basically. First, it is accepting electron. Second, it is removing the oxygen, and it is getting oxidized because it is donating electron, plus its oxidation number is increased due to that reason, and it is having O now. Clear? Now this is the reaction of phenol with zinc dust. So in the next reaction, we will see Reamer-Timmer reaction and Kolbe. Okay, we will see Reamer-Timmer reaction and Kolbe, and then we will see oxidation reaction also. Okay, so we will see these two reactions. Plus tomorrow we will also see how does this acidity of phenol work. So in this class I have not moved to this acidity of phenol, although we have seen a wide application of this acidity of phenol. So we will try to compare the acidity of your phenol with alcohol, and also we will see what is oxidation and reduction reagents that are used to and fro for reduction of these groups. So I think this is very important to know about each and every reagent that is appropriate for a syllabus. I would not just push the reagents whichever I want. I will use only that reagent which are relevant to your chapters. Okay, so we will see some common reagents that are used for the reduction and oxidation purpose. So we'll see it tomorrow. Clear? So this was for today's class. So we have covered half of this reaction with phenol, reaction of phenol, yes. So we'll cover the rest of this Kolbe's reaction, oxidation reaction, and Reamer-Timmer reaction in the next class. Thank you.